All right, we are ready to get started. Sorry for the delays. So welcome to our next CU Prime talk. My name is Tyler. It's CU Prime, if you have not heard, is a student organization of the physics department that's devoted to diversity and inclusion and making a welcoming environment for everyone. So for everyone in person, be sure to eat pizza if you haven't signed in on the laptops already. And be sure to do so. You can also scan this QR code. And yes, so one of the things that CU Prime does is a talk series where we try to create a way for you to hear about all the cool research happening at the university and what it means to be a scientist in all of the aspects of the word. So today we're going to hear from Rose Smith, who's going to be talking about some of her work as an astronomer. It should be super exciting. And with that, I will let you take it away. Wonderful.
Thank you, everybody. Yeah, so Arrokoth and some other stuff. A journey to the unknown. To start off, a little bit about myself. I graduated from Ralston Valley High School, about a half an hour south of here in Arvada in 2013. I then graduated from here, University of Colorado Boulder in 2016, with a degree in astrophysics. I then worked down in Golden at Software Fisk, which is a telescope manufacturer, for about 4 years. I worked really closely with SWERI and NASA. If anyone doesn't know who SWERI is the Southwest Research Institute. They're headquartered in San Antonio, Texas, but have a satellite office down on Pearl Street. The satellite office on Pearl Street does all of their planetary science. So they're a non-governmental, non-educational research institute. So their main focus down at their San Antonio office is like materials research and like car testing and all sorts of engineering stuff. But they also do planetary science and astrophysics out of the office here in Boulder. And I've kind of gotten to know a lot of the folks over there and I've worked with them. And they're the ones behind the science of both New Horizons and Lucy, which are the two missions I worked on with them. And then since 2014, I worked with the observatory on campus, Summers Lodge. And since last summer, I've actually been the manager of Summers Lodge Observatory. So unlike most CU Prime Talk speakers who are oftentimes grad students or postdocs or things like that, I'm actually a staff member at the university. Yeah, so New Horizons. I'm sure most of you probably heard about New Horizons, but for anyone who hasn't, New Horizons is NASA's mission to explore Pluto and then the outer solar system. It was launched back in 2006, with its flyby of Pluto occurring later in 2015. And then we finally got around to Arrokoth, the object that I'm going to be talking about today, in 2019. Couple quick fun things about New Horizons. New Horizons never entered Earth orbit. The rocket that launched it was so powerful and New Horizons was so lightweight that it had too much velocity to ever enter Earth's orbit. It just immediately booked it out of the Earth's gravitational influence and headed out into the outer solar system. At its maximum velocity, New Horizons is traveling at 58,000 kilometers an hour, or 36,000 miles per hour. It's one of the fastest man-made objects. So the Apollo astronauts took 3 days to get to the moon. How fast or how long do you think it took New Horizons to cross that same distance? Going its crazy velocity, it never entered orbit. Any ideas? Yeah, a few hours, maybe? 9 hours. So it took 9 hours to reach the orbit of the moon. On its way out to Pluto, it also used a gravity assist off Jupiter, where basically it steals. Sorry. It basically stole a little bit of Jupiter's orbital velocity in order to add its own velocity. Yeah. Sorry, I have to advance the slides on both computers. So if I forget, please let me know. We get to Pluto, we get the beautiful pictures of Pluto, the nice little heart on it, everything's hunky-dory. But now what do? What's next? Well, what's next is we're going to search the outer solar system for something interesting to send the probe to that we spent, $1 billion building and sending to the outer solar system, we might as well get some more mileage out of it. So we sent Hubble on a mission to search for things to send our spacecraft to. And what did we find? Well, we found this little speck in the star field that was in line with where New Horizons was already headed. These are the actual images from the Hubble Space Telescope. There's 5 images in sequence, and you can see the little blob progressing through the sequence. And you can see this is the same image with all five images co-stacked, so you can see the blob at all 5 points. So this is the actual Hubble Space Telescope data for the discovery of Arrokoth. Note at the time, by its designation 2014 MU69, which means that it was discovered in 2014. The mission launched in 2006. So when we discovered the object that we were going to fly to was 8 years after the launch of the mission that was actually going to go visit it. A little bit backwards in terms of mission planning. So a couple of interesting things about Arrokoth, as viewed from the Earth, of course. It has an apparent magnitude of 26.8, which either you know what that means and you're laughing because that's incredibly dim, or you don't know what the magnitude scale is. The astronomical magnitude scale is really super duper extra dumb. It's an inverse logarithmic scale with a base of 2.5. And if you have no idea what that means, basically every 5 magnitudes is 100 times dimmer. The brightest thing in the sky, the brightest star in our sky is about magnitude 0, and the dimmest thing you can see with the naked eye is about magnitude 6. So if the dimmest thing you can see with the naked eye is about magnitude 6, and Arrokoth is magnitude 26.8, how much dimmer is it than the dimmest thing you can see in the darkest sky? Discuss with your neighbor. All right, answer? 705th exponent. Final answer. Incorrect. Correct. It's 100 to the 4th. Which is? It's 100 million times dimmer. So if it's 26 minus 6 for what you can see, 20 magnitudes, that's 4 sets of 5 magnitudes, so 100 to the 4th. 100 million times dimmer than the dimmest thing you can see with the naked eye. It takes about 300 years for Arrokoth to go around the Earth. And if you know the astronomical unit scale, its centimeter axis is 44.5 astronomical units. It's really, really out there. What? Still talking about this one slide. So, we have a problem. Here's our solar system. Here's Pluto, way, way, way the hell out there. And then there's 2014 MU69 Arrokoth. And we have our little spacecraft, New Horizons, headed on out there. What do you think kind of problems we might have in getting our spacecraft to an object that no one's ever been to? We've only ever gotten a couple of very rough images from the Hubble Space Telescope, and that's pretty much all we know about it. What problems do you think we'd have trying to get our spacecraft there? Go ahead and discuss. All right. Ideas? What kind of problems might we have?
In case something goes wrong, like you need to send it basically additional data about where the object is because it's so far out there that a signal would theoretically never reach.
So that's actually a huge problem that's completely unsolvable. Because the communications delay, because of the speed of light time lag, is in the like tens of hours for this part of the solar system. And a flyby might only last 30 minutes. So once you're in the flyby stage, you have no ability to modify anything at all. Other ideas? Problems? Yeah.
There's no GPS.
Yeah.
We don't know where we are.
Well, so we know where we are because in the spacecraft, we have cameras that are looking out at the rest of the solar system. But how well do you think we know where Arrokoth is? Any other ideas for problems we might have visiting this faraway place that no one's ever been? Yeah.
Might want to know how big it is.
Yeah, that would be a good question. Yeah.
How would we know looking at Arrokoth and see?
We-
Like, I mean, if we took like images, but we couldn't really get a good look at it, couldn't it just be another big space object that we just didn't notice in our camera? Or
So
weren't paying attention?
we actually don't care that it's this, like, we just want to find something that's out there. So as long as there's something, we'd like to go look at it. But like, that's kind of leading into what I wanted to get to. So the first question is, where exactly is this thing that we want to go visit? We need to know really, really precisely how it's orbiting so we can know where to send our spacecraft to get there. And the other question really is it actually safe to go there and conduct this flyby? So on the Hubble images, we just saw this little point of light, totally unresolved. It's a point source. There's no information. Maybe it's an object. Maybe it's a cloud of little objects. Maybe it's a cloud of dust. Maybe it's two objects orbiting each other. Maybe it's two objects stuck together on end. Hint, hint, wink, wink. Maybe it's something that we have no idea and have no expectations of. We don't really know. If it's a cloud of pebbles that's reflecting that light back to us and we try and send New Horizons in, well, we might just smash into the pebbles at 58,000 kilometers an hour and not have $1 billion spacecraft. And Ellery's thought earlier, knowing what size it is also helps us determine how we need to point the cameras, because if this time lag of sending updates to the spacecraft is in the tens of hours and the flyby event is in the scale of minutes to hours, we have no ability to change how the cameras are pointing once we see what's going on. So we have lots of unanswered questions, and if the Hubble Space Telescope can't see something, you're pretty much out of luck. If the Hubble Space Telescope sees your thing is a little blip of light on the edge of detection, there's really only one option. And the answer to all of our problems is occultations. So occultations are kind of like solar eclipses or eclipses in general, where we have something passing in front of something else. It's also like a transit. So like the transit of Venus or the extrasolar method for discovering, the transit method for discovering extrasolar planets. In this case though, we have a random star in the night sky, just some random star, usually not even one you can see with the naked eye. We have the object that we're actually interested in. This diagram is labeled as a comet, but it could easily be an asteroid, it could be a Kuiper belt object, it could be a moon, doesn't matter. This is the thing we're actually interested in. The star doesn't matter. And then we have observers on the ground. What we're actually looking for to observe is the shadow cast of this star's light by the object we're interested in on the surface of the Earth. So we're looking for the shadow of an object that's like tens of kilometers across of just the light coming from a single star in the night sky. So it's not like an eclipse where all of a sudden the sun goes out and it's dark. It's a single star you can't see with the naked eye, blinks out for 2 seconds. That's the event we're interested in. But if we can observe that event in just the right way, not only can we get extremely precise orbital parameters of that object, we can actually get a rough outline of the shape of that object, and we can quantify whether or not it's actually a solid object, or if it's a debris cloud, or if it has a ring structure, or anything like that. Or at least if we can't rule those things out, we can set lower limits on how much of that material could exist, which allows us to make safety calls with our billion-dollar spacecraft that's been traveling for more than a decade, which is rather important if you're the bureaucrat at NASA who has to sign off on risking that spacecraft. So the thing with occultations is when you have a solar eclipse, you have the path that goes across Earth's surface where you need to observe it from. So like for the 2017 solar eclipse in the United States, you remember there was that path that went through the center of the country that you had to actually go to if you wanted to see it properly. The same is true here, except that the size of that path is relative to the size of the object you're interested in. So if the object is 20 kilometers across, that path, that shadow is 20 kilometers across. And it's just projected somewhere random on Earth. So if we're interested in this one particular hyperbelt object and we need to get an occultation and we need to get it in a relatively short amount of time, we discovered it in 2014, the flyby was going to happen in 2019. We need to go wherever we need to go to get to that shadow. And not only do we need one telescope, but we need a whole bunch of telescopes on the ground because we need to be able to, A, actually catch the event. Our prediction of where that shadow isn't super accurate. Say it could be within like 100-kilometer band on Earth's surface. So we need a whole bunch of telescopes spaced out to make sure we catch it. But also the way that we get the profile is by having multiple telescopes. And I'll get into that later once I have a better diagram to show you exactly how that outline gets formed. So the lead up to the Arrokoth flyby, we identified 4 events that would suit our needs for a star bright enough that our portable telescopes could actually observe it. And we're in places that were actually possible to observe. You know, if the event goes across Antarctica, it's pretty unattainable. The weather there is not the best for optical observing. So those 4 events that we identified are as follows. The very first one passed through the tip of South Africa, through the country of South Africa, and through the center of Argentina and Chile. The second event passed through the South Pacific. The third event passed through Patagonia at the far southern end of Argentina and Chile. And the fourth event passed through Western Africa and the North and South America. Those are our only 4 chances to catch this. If we don't catch at least 2 of these events, then we basically can't send the spacecraft to Arrokoth, and we can't explore the outer solar system anymore with New Horizons. So these are very important missions that have to go off without a hitch, and we really need the data from more than one. And the event only lasts 2 seconds. So if there's a cloud in the way, there's no do-over. If you don't set up the telescope right, there's no do-over. You have one shot to get the data. And you just lug your telescope to another continent for your one shot. So I went to South Africa. And this was in 2017. I was a year out of undergrad. And oh boy, did I feel imposter syndrome. So we went to South Africa. This is the team setting up in Cape Town, practicing with telescopes during the day. They're really cool telescopes. They're called Dumsonians, if any of you know what that is. Basically, it's a big, dumb reflecting telescope. It's a very simple design. They're also typically collapsible, so we can collapse it down into a smaller area. Because this telescope is 16 inches across, we need like 25 of them, and we need to get it to like Cape Town, South Africa. So the only way we can do that is with a giant shipping container and like sea freighting our telescopes months in advance. The bottom left photo is a little hard to see. It's the farm that I got to set up at night for my observations. Yeah.
Don't they have telescopes in South Africa?
So we need to have identical telescopes for ideal performance. We need to have large portable telescopes. And the commercial supply of those is very limited. We also need telescopes that we know how to use and are proven to work reliably. And so while there are sort of the ability to buy telescopes or acquire them locally, they would be hodgepodge from amateur astronomers and things like that. We do use fixed like, permanent observatories, but those we can't set up every 10 kilometers in the middle of the bush where we need them. So like the South African National Observatory at Cape Town did observe this event, but they weren't in the right zone to actually get the data we needed. They were just serving as an outer bound.
Okay.
So yes, we use locally acquired telescopes, but they can't fulfill the main mission of rapid deployability anymore. That makes sense.
You guys made those.
Those telescopes are actually commercially available.
Okay.
There's a commercial company that produces them for the amateur community. And when the team called them up and like, can we buy 25 of these? They're like, we sell like 3 of these a year. You want how many? You're who? You're NASA? What? Yeah, they were pretty befuddled. Yeah. So there's all of us astronomers. We're in teams of 2. We're getting sent out into the South African bush. We're basically told, here's a line on the map. You need to set up your telescope on that map. You need to acquire data from this time to this time. That's your job. Figure it out. My teammate and I, we got in our pickup truck with our telescope. We drove around, in, bush in South Africa. We come up police station, just as someone to talk to the police chief, and he's like, oh, you want to set up a telescope in our town? Oh, there's a farm. They're down on the road. I'll show you on the map. I think they've got a good spot for you. So we drive down there. That's the farm in the bottom left photo. Knock on their front door. This elderly couple comes out and says hello. They're like, oh yeah, so we're from NASA. We'd like to set up a telescope in your backyard. And they're like, oh, a telescope. Oh, we have a telescope pad out back. Would you like to use that? They had a poured, perfectly level concrete pad with a power outlet, dimmable red lights, and a telescope here, which we didn't need because our telescope was designed to be set up on a field, but they sure had it. Yeah, no, it literally doesn't get better. And even better, the woman brought us out tea and snacks in the middle of the night when we were observing, on both the practice night and on event night. She didn't want us getting cold out, so she brought us some tea. All of our other teammates were slumming it in the back of a farmer's field or on the side of the road. We had tea and cookies and a lit telescope pad. The day before the event, though, someone back at NASA HQ got a little nervous because they're like, you sent how many people into the bush in South Africa by themselves in the middle of the night? That doesn't seem safe, does it? So what did they do? They hired private military contractors to protect us. They literally hired a whole team of private military contractors armed to the teeth that their day job was fighting poachers in Central Africa. These guys meant business. They were really scary dudes. So on event night, this is my team. This is myself. This is my partner, Con. This is the couple who owned the farm. They wanted a picture with us with the telescope. And then this gentleman, who is clearly much taller than I am, he was the leader of this little brigade of private military contractors. He was 6'6", 400 pounds, had this huge handgun. It was this big on his leg. He meant business. His colleague here, also really tall, he was 6'4", 6'5". His name was Skull. That was definitely his birth name. He had a combat shotgun when she was just waving around. I was more scared of them than I was of the animals or anyone hurting us. Anyway, as it turns out, Skull really into astronomy, asked a lot of great questions, got really into the science. Not a joke. He was really cool. That's almost impossible to see. The telescope is set up there, and those 2 bright lights are my laptop and the other laptop that I was using to control the telescope. I was using the big case that our telescope came in as a desk. I was sitting there, my little camp chair that I brought all the way from Colorado, working on the telescope, and Skull comes over and starts asking questions. And he just plops his shotgun down right on my little desk. I'm like, oh, hello there. Yes, I'll answer any question you like. Anyway, they're actually great guys. It's just really weird. House took this beautiful Milky Way shot while I was there, killing time. So we had a great time, lots of cool adventure. We ended up having decent weather. We got data, the team got data. All this work, all this effort, flew to South Africa. Oh, and don't worry, while my team was in South Africa, there was a second team in Argentina as a backup for the weather. And so we were overlapped in position. So that way, if the South African team was spotted out, the Argentina team would still see it. So all this effort, 50 astronomers, 20 telescopes, 2 continents. The result? Nothing. Didn't see an occultation. Absolutely nothing. Nothing at all. Well, all you can do is have fun.
Well, okay, so what?
I'll get to that in a minute. Okay. But went on a safari, saw the penguins, had a blast in Cape Town, but no data. So, second try. Remember that event that was just out over the South Pacific? How do you think we're going to observe that one? Discuss. The sun was up over South America, so it was unobservable. Remember, we need to be on at the precision of 10 or 20 kilometers of where we need to be.
There's nothing.
Yeah.
All right, ideas? So boat's gonna be pretty unsteady. It's gonna have rocking, really hard to track the star with the rocking chip underneath it. To answer the question about islands or the land, you can see that it does cross a little bit of South America. When it was over South America, the sun was still up, the stars really dim, so we couldn't see it, and there were no islands that intersected this line anywhere along its path. Any other ideas for how we can observe it? What was that? Hijack oil rig. Unfortunately, no. Yes? No, we need a 16-inch telescope. The rocking of the ship would make it impossible to track the star. Got it on the first one. So the answer is Sophia. Sophia is a collaboration between NASA and the German National Space Agency. It is a Boeing 747 with a giant hole in the side with a 2.2 meter telescope sticking out the side. No, this is still in operation.
They're talking about defunding.
They are talking about defunding.
Yeah.
What do you think this plane's day job is?
Is it one of those that have
Does it have? Does it have to have a day job?
It does, well, it costs a shit ton of money, so it better have a day job. Nope, it does astronomy.
it's never in space.
Yes.
Like, so we can decide.
So Sophia's day job is doing ultraviolet astronomy. So the Hubble Space Telescope, in addition to being an optical telescope, is also an ultraviolet telescope. Because we can't observe ultraviolet light very well from the ground because luckily the Earth's atmosphere protects us from that for the most part. Otherwise, we'd be pretty dead. But it means that we can't do ultraviolet astronomy from the ground. So, it's really expensive to build Hubble, and it's really hard to change out the instruments on Hubble to do ultraviolet astronomy. So NASA had the bright idea to put a telescope on a plane, fly it above most of the atmosphere, and you can still do some ultraviolet astronomy from this platform. But if you're the New Horizons team and you're like, hey, we need to observe this occultation in the South Pacific. Can we borrow Sophia for a couple of days? That's the kind of request that NASA's like, sure, go ahead. So Sophia observed it and we got data. We only had the 1 point because we only had the one telescope. There's only one Sophia, but we did get the observation, and that allowed us to refine the prediction of the object's path, which allowed the next occultation, the one that went through Patagonia, to be much more successful. We got a lot of data. So I unfortunately didn't get to go on this campaign, so I don't have any fun stories of the event, but I can use this as a great opportunity to talk about the science a little bit more. So what the image you're looking at is each one of these lines is the view from a single telescope on the ground. This axis is duration in time. This axis is position on the Earth's surface. Along this axis, each tick mark here, each line is, I think for this campaign, there were about 5 kilometer physical spacing, something on that order. And so the shadow, as the object passes over us, will only work. So we're trying to bound the shape of that shadow as it's passing over the surface. And so if a telescope doesn't see an occultation and the next one does, that means the edge of the object had to pass somewhere between those 2 telescopes. Time is just how long the star blinked out in the night sky. And then the position along this is the absolute time as synced by GPSs. The cameras that we use actually have a little GPS receiver that tag every single frame with the exact time that that image was taken. So that way all the data from all the telescopes can be recombined later in plots like this. So what we're seeing is how long and when each telescope on the ground saw the star blink out. And from that, you can piece out this very rough outline of what Arrokoth looks like.
This is from the third, not from the second.
This is from the third. So the second one, yeah, so the second one only has one of these lines.
Yeah.
And in fact, it only got a little teeny tiny blip. So we only caught just the edge of either side of it, and that's it. And we'll see that plot a little bit later. This is the third one. We actually got a bunch of data, and we got this very rough outline, but we also got a good size constraint for the maximum size this object can be. It has to fit between this and that top line in terms of distance and size, and it has to fit between the durations of all of these chords. Any questions on this? This is probably the toughest part of the science. Yeah.
Worry about it changing orientation and suddenly becoming much bigger or smaller. Like if it's big spike facing us.
Yes, so gravity doesn't like that, but yes, technically you could have something that's very elongated, and if it's rotating, then you could end up with, yeah, it could be way bigger in one axis and not another. This is why multiple occultations can be really good, because you can get it from multiple perspectives. And if you have enough data, you can actually slowly create a 3D view of the object, because you have a bunch of little slices running through the object, and if the object's rotating, you could create a 3D view, but that takes an enormous amount of data. So yes, this puts a limit on a 2-dimensional cross-section that happened to be facing us. So it should, gravity says that this should be the maximum size, but yes, that's not an absolute. Any other questions right now? Yes.
What about the missing line?
The missing line was someone who did not operate their telescope properly. So actually one last thing. So we have this rough plot. You can see there's 2 red circles, which was the team's best guess for what the object looks like. And when we actually see the object, this was remarkably close to what the object ended up looking like.
I think anybody had like second guesses, but they thought they found it out because it's just 2 circles stuck to each other.
Oh, we were like, what the hell is going on? This makes no sense, but the data is the data. So that 4th attempt through Western Africa and through the north of South America. This is another one I got to go on. I was deployed to Senegal in Western Africa. There was a second smaller team deployed to Colombia, but the primary team was in Senegal. Got some cool photos of my travels through Senegal. Mangoes out of this world. So if you're Senegal, you're a small West African country, and well, so we learned a little bit from that first occultation in South Africa that maybe we should like plan ahead, maybe like call the US State Department, be like, hey, like 40 people from NASA are going to this random country. Do you want to maybe help us out on the planning? So by the time we get all the way to Senegal, the US State Department has like pre-screened everything. They've like put us through training on like escaping minefields. Not a joke. Not a joke. And they've set up through diplomatic channels, you know, like assistance from the Senegalese government and things like that. Well, I guess it's kind of a big deal if a bunch of people from NASA show up in your small West African country, because we got an invite from the president of Senegal to come hang out at his palace. Wow. This is the Senegalese presidential palace. This guy in white is the president of Senegal. And that's me. This is Mark Bowie, the team leader. And this is the US ambassador to Senegal. We rated pretty high in terms of diplomatic visits that year for Senegal. They cleared all the traffic on the roads for us. They had Senegalese police and military clearing the roads so we could just drive down the middle at high speed. We had US diplomatic vehicles, you know, riding in our convoys, you know, like with the little embassy flags and the whole 9 yards. Yeah, it felt pretty special.
Yeah.
Cool. So another problem, Senegal is not a country that speaks English. Senegal is a former French colony, so French and then a number of local dialects are really the only local languages spoken on the ground. And the main team is mostly from Boulder and from across the US, and not a lot of us spoke French, let alone Senegalese native dialects. So for this one, we called up the French National Space Agency. It was like, hey, can we borrow some folks who can come help run telescopes and do some translation for us? They're like, yeah, sure. We can send like 20 people down with you. So most of the experienced astronomers from the team here were teamed up with someone from the French National Space Agency or from other French astronomy organizations. The guy I worked with, Jean-Luc, was an astronomy journalist in Paris. And so he was an excellent astronomer in his own right and was also able to help translate anything I needed into French. And then we also had local guides who spoke French and various local languages. That way we could communicate with anyone we needed on the ground. Yeah, so, you know, we were traveling in these convoys. There's our telescope setup. You know, these are the same telescopes that we took to South Africa, and now we've taken them to South America and now back into Africa. These telescopes have seen some miles. Instead of private military contractors, the Senegalese government was gracious enough to provide their own soldiers to protect us. So these are some Senegalese soldiers on deployment or serving as our bodyguards. Some of them may have maybe set up a checkpoint on the road next to the telescope and asked for bribes for people to drive by. If you're in a country that doesn't have a lot of law enforcement and you're a soldier with a gun, I guess you can just get away with that. Yeah. Like you do. Yeah, it's a bit awkward, but it's not a lot the astronomers at the site could do about that. Another cool thing about the occultation in Senegal is, in addition to us on the ground, the Hubble Space Telescope also observed this event. So it wasn't in position to actually see the main shadow, but it was able to get close enough that it was able to set a really, really low bound on the amount of debris that might have been around Arrokoth. So it wasn't able to help us with the actual data on the main object, it was able to tell us how much stuff might be in the way further away from the object itself. After we got our data, once again, we loaded our telescopes back into the shipping container. We went out, did some exploring. This is called the Pink Lake. Under the right conditions, there's a bunch of algae in the lake that turn it bright pink, like the pinkest pink, but it's the entire lake. Really crazy place. Didn't get to see it pink, but it was pretty cool. At that lake, I found a pair of snow skis. Not sure why. We're, just south of the Sahara Desert. Not a lot of snow. It's like 10 degrees north latitude. Snow skis. Yeah, Africa. So we got our data. Now it's time for the flyby. Here's New Horizons. Here's the instrument view, and here is the spacecraft, and showing the fields of view of the instruments onto the sky. And then this is a simulation of what each of the different cameras was seeing as we're approaching and flying by Arrokoth. So I said at the beginning, or towards the beginning, that it only took about 30 minutes for the best part of the flyby was going to occur. And so we were just taking as much data as we possibly could as fast as we can, because it's not like we could slow down. We don't have fuel for that. So we got to just get as much data as we can as we go by. So let's watch it go by. So not really seeing anything. All right, switching to the high resolution. Oh, there's a little speck there. Oh, speck. Okay, we're tracking it in. Speck. Oh, it's getting elongated. Oh, a little more. Oh, it's a bean. Oh no, it's that weird snowman thing we saw. Oh, hey, look, there it is. And it's gone. That's our data.
That was a simulation.
What?
That was a simulation.
That was a simulation, yeah. This is just a simulation of what the data acquisition sequence looked like. Obviously, there's a lot more data. There's spectrographs, there's other instruments, but the amount of time we were actually taking data was incredibly short in comparison to the decades that the spacecraft's been flying, and the weeks and weeks we spent on the ground trying to get navigational data for computations. So we collect all this data, just taking as much data as we can. How long do you think it took to download that data from the outer solar system back to the Earth? For scale, it was in the tens of gigabytes of data. Discuss. All right, who's got a guess?
10 days.
Anyone else?
3 weeks at least.
30 minutes.
It took 20 months to download the data. 20 months. The Wi-Fi in the outer solar system isn't very good. The data rate, for anyone who's curious, averaged between 1 and 2 kilobits per second. 20 months to get our data back. It was a similar amount of time to get the data back from Pluto for the New Horizons flyby. The Wi-Fi in the outer solar system is really, really slow. It makes dial-up look like high-speed internet. So, what did we get? Well, we got this. These are the actual images we got of Arrokoth during the flyby. We were only able to get one side because as we were flying by, the object wasn't rotating fast enough for us to see both sides. As you see on the left, the change in quality as it rotates is based on the distance of the spacecraft. So the really fuzzy image is when the spacecraft was far away, and it only gets really in focus once we actually got in nice and close to the object to see it. So we visited another thing in the Kuiper Belt. This is the furthest object that humanity has ever seen up close. This is the most ultimate frontier, the furthest place that humanity's ever visited. Totally unexplored part of the solar system. This is just absolutely remarkable that we can have this image at all. So, about that shape. It's not even two spheres that are stuck together. It's more like two discs that are stuck together on their edges. It's really weird. And my title's titled A Remarkably Shaped KBO, Kuiper Belt Object, but is it remarkable? How do we know? We've seen Pluto, we've seen its moon Charon. Those are big enough to collapse into proper, or, to form into proper spheres. This is the only small Kuiper Belt object we've ever seen. Maybe they all look like this. Maybe they're all two disks stuck together on edge. It's not very likely, but we only have a sample size of one object to compare it to. So
We have notations.
well, we have a couple, but they're really, really hard to conduct, especially with enough targets to get enough of a profile to really determine that. So that would be certainly one option to get more sample size, or maybe we should explore the Kuiper Belt more. Maybe we should send some more probes out there. But until we do, this is what we've got. And it's hard to know if this is unique, if this is the one oddball, or if this is the most common way that things are out in the Kuiper Belt. Let's go back to the results of our occultation campaigns. These are the 4 plots from the 4 campaigns. There's a really sad plot from South Africa and Argentina. Absolutely no data. There's one line all the way at the top. It's hard to see. That was the farthest south observer we had. Totally missed it. Just nothing. This is the Sophia, the one over the South Pacific. We're not sure which end of the object we actually ended up getting. So this is just showing it might be here or it might be the other end. We're not really sure. That third occultation, that really great one where we got that estimated profile. This white outline is the actual outline of the object as we know now, overlaid in the correct orientation of when we observed it during these occultations. So that's why they're in different orientations in the different plots. But if you look, our data lined up incredibly well in comparison to what we know the object actually looks like. And then in Senegal, we were only able to get 2 cords of data, but that at least really helped us nail down the orbital parameters, which really helped us nail that really close flyby of the object. So, the name, 2014 MU69 was just the initial designation. A couple of other catalogs. Originally, the team was calling it Ultima Thule, which sounds cool. It means beyond the borders of the known world, like the most beyond the borders of the known world. Unfortunately, after some more research, a bunch of racists also like to use that term. So we dropped that like a sack of hot potatoes, and we renamed it Arrokoth. Arrokoth is a word in the Popon language, which is the native peoples in the region around what's now Maryland and Virginia. The word means sky. We chose that because that is the rough location of where Arrokoth was discovered, which is the control room for the Hubble Space Telescope. So, what's next for occultation science? Well, the next big thing is the Lucy mission. The Lucy mission launched last fall out of the Kennedy Spaceport. It's a mission to explore the Trojan asteroids of Jupiter. The Trojan asteroids are 2 clusters of asteroids that orbit at the distance of Jupiter, but in front of and behind Jupiter in Jupiter's orbit. They're held there by the combined gravity of Jupiter and the Sun in what's called the Lagrange points. In this case, the L4 and L5 Lagrange points, if you know anything about that. But basically, they're just trapped in these islands of stability in terms of gravity. And they are thought to be some of the earliest remnants left of the solar system. They're very isolated. They don't get perturbed very much. So they're probably very, undamaged from the earliest stages of formation in the solar system formation. And we'd like to go there. We'd like to observe these objects. This is another place that humanity has never been. We've never observed or visited a Trojan asteroid. We've been to the asteroid belt. Now we've been to the Kuiper Belt. But this is probably the biggest area of the solar system that we've never, ever been at all. The mission Lucy is actually not an acronym. It's actually just the name Lucy, which is a bit weird for NASA, for astronomers in general. Gotta have acronyms, right? Well, the mission is actually named after the Lucy's fossil specimen, which is thought of as like a missing link in the evolution of humans. And we think that the Trojan asteroids might be a missing link in the formation and development of the solar system. So that's how the mission got its name. The mission is really interesting. It's going to visit 7 Trojan asteroids. over its like decade-and-a-half long journey through the solar system. It has this absolutely crazy orbital path with a bunch of gravity assists and these two big free return trajectories. So it goes out, loops around through the Trojans, and then comes back just based on gravity. It doesn't have to do a whole lot of, it doesn't have to expend a whole lot of fuel to make these maneuvers happen. And it's going to visit 7 objects, which is also unprecedented. The most objects visited by a single spacecraft that aren't like big planets that were in like amazingly perfect alignment is like 2 or 3. So this is a pretty cool mission and a special opportunity that we're able to visit 7 asteroids with the same launch. What it means though, we have 7 objects, we need occultations for all of them, and multiple occultations for all of them. That's a lot of occultations. So I myself have done 4 occultations in support of Lucy. I think there's been about 7 or 8 in total, with the most recent 2 wrapping up only a couple of weeks ago. The 4 that I have conducted are these 4. One that went through Arizona between Tucson and Phoenix, one just north of San Antonio, a double occultation passing over the United States. This one is 2 of the objects that Lucy's visiting are actually a binary pair of asteroids. And so this is the path of both asteroids passing in over the United States. And the final one was last fall in Spain. So free trip to Spain. Wasn't half bad. One cool thing from the San Antonio occultation is, so this was 2017. So, no, not 2017. This is 2019-ish. So I'm only a few years out of undergrad. Like I'm still pretty young. I'm only 26 now. I double check the math on the occultation prediction every time I go up one of these, just to make sure. It doesn't hurt to double check, right? It was wrong. The official prediction from the mission team was off by about 30 minutes in time and about 100 kilometers in distance. Our entire setup was only going to measure about 75 kilometers on Earth's surface and was only going to take data for 15 minutes before and after. So if we used their prediction, we would have gotten absolutely no data whatsoever. I double checked the math. I showed that it was wrong. They found the bug in their code. They updated the prediction model to match mine. We got the data. It always pays to speak up, even if you're the youngest person in the room. As a part of the mission team, I got to go to the launch of the Lucy spacecraft last fall. It's pretty awesome getting invited out to the Kennedy Spaceport, getting to go behind the scenes and see the rocket launch, get to tour the launch pad. Pretty awesome. Awesome, awesome launch. A ton of fun. Now what's really cool is young scientists and undergrads often get invited to go on these campaigns. You don't always get to go on the glamorous ones, but I think it's pretty cool science. And so if you're interested, stop by after and ask for a business card, and I can help get you connected to the people that might make it possible for you to do this too. That's it. Any questions?
All right, thanks guys. So we have a quick survey. If you want to give feedback on this talk, you can scan that QR code with your phone. And yeah, otherwise, feel free if anybody has any questions right now. Yeah.
Why was back from your beginning? Why were there only 5 frames on that Hubble data? The first observation.
Yeah. So basically, the way the observation campaign for discovering, so we had to discover objects to look at. We didn't know of anything that was in New Horizons way. So basically, we tasked Hubble to just take a bunch of images in and around the area that we knew New Horizons was going to be passing through. And so we just took little sequences of images to look for things that were moving through those images. And that's all automated. And so only later, after the data was downloaded and processed, did we go, oh, hey, there's actually something in this frame. And so 5 frames was enough to positively identify that something was there and moving at a speed that we cared about. And so later on, we're able to get some additional data, but without the applications, it's really hard to nail down the really precise orbital parameters we need.
Horizons cook out, is it just like on the way?
So right now, it's just coasting off further out into the solar system. There has been some talk of trying to do a second campaign to search for things, but we probably would have found it with the first search. So there hasn't been a whole lot of interest in spending a whole bunch more of Hubble's time looking for a second target to visit or a third target to visit. So right now, it's just kind of coasting. They're using it for taking measurements of like, the outer solar system, like the way Voyager probes are being used right now, but it's not doing nearly as much since there isn't anything it can really realistically visit. It also has very little fuel left, so its ability to correct to get to something is very limited. Questions?
Okay, well, if you have more questions, feel free to come up afterwards. We can stick around for a little bit. Otherwise, thanks everyone for coming. We'll have our last talk of the semester 2 weeks from today. We'll see you then. Oh, yes, wait a minute. So there is one more announcement. So next week, we have a mentorship program event. So they're putting together an industry panel from people who have graduated from CU who are going to talk about their experiences. What can you do with a physics major? Where can you go afterwards? And so this is going to be in this room as well. There's going to be pizza as well. If you want to join on Zoom, you can do that in addition. And yeah, I can provide more details to everyone if you have more questions, but that'll be next week at the same time, I believe, in this place. Okay. Thanks. Bye.